In this module, you will learn about surface tension and surface energy. When we blow soap bubbles, we observe that each bubble acquires a spherical shape or an almost spherical shape, irrespective of its size. It's the same with a drop of any liquid, such as a drop of molten wax or oil on water. In all these cases, a force tries to reduce the surface area of the liquid to a minimum. For a given volume of a liquid, the shape that contains the least surface area is a sphere. Force due to surface tension makes a drop or a bubble assume a spherical shape. Consider a liquid, say water, in a beaker. The molecules in the beaker are free to move within the given volume. A liquid stored in a container has a free surface. For a liquid in a container, there are two types of forces of attraction. The first one is the force of attraction between the molecules of the same substance, which is referred to as a cohesive force. The force of attraction between water molecules is a cohesive force. The second one is the force of attraction between the molecules of different substances, which is called an adhesive force. The force of attraction between water molecules and the molecules of the glass container is adhesive. Similarly, the force of attraction between water molecules on the surface and the air molecules surrounding them is adhesive. Cohesive forces are short-range forces. Their magnitude decreases with distance, and they become negligible when the distance between the molecules increases beyond 10 to 15 molecular diameters. Thus, we can assume that these molecular forces act on a given molecule within a sphere with a radius of about 10 to 15 molecular diameters. The sphere within which the molecular forces act on a given molecule is referred to as the sphere of influence. For a molecule that is well inside the liquid, the complete sphere of influence is within the bulk of the liquid. The net force on such a molecule is zero, as it experiences an equal pulling force in all directions. For a molecule close to the surface of the liquid, a part of the sphere of influence lies above the surface. As cohesive forces are greater than adhesive forces between liquid and air molecules, and since there are a greater number of liquid molecules within the sphere of influence than air molecules, there is a net downward force. For a molecule that is on the surface of the liquid, half the sphere of influence lies inside the liquid and the other half in air. There are a greater number of water molecules in the lower half of the sphere of influence than the number of air molecules in the upper half of its sphere of influence. Hence, the molecules experience a net downward force. The molecules coming from the bottom of the liquid to the surface have to overcome this net downward force and hence have potential energy called surface energy. Hence, all the molecules near the surface and on the surface have greater energy than the molecules deep inside the liquid. The liquid surface tries to contract. That is, it tries to minimize the area to lower the energy of the surface, as this offers great stability. Hence, the liquid surface is in a state of tension and behaves as a stretched elastic membrane. This tension is proportional to the length of an imaginary line along the surface. This force per unit length acting on an imaginary line drawn on the free surface of a liquid is called surface tension. If the magnitude of the force is F, then we define surface tension S of the liquid as S is equal to F by L. Thus, the SI unit of surface tension is Newton per meter and its CGS unit is dyne per centimeter. Hence, 1 Newton per meter is equal to 1000 dynes per centimeter. There are numerous examples available to illustrate surface tension in liquids. Water striders, a species of insect with long legs, float on still water surfaces without drowning, as the water surface acts as a stretched membrane due to surface tension. Now let us derive an expression for the surface energy of a liquid. Consider a U-shaped open wire loop fitted with a wire of length L, connecting ends A and D. This wire, AD, closes the loop and can slide on its arms AB and CD. The closed loop is dipped in a soap solution and taken out to form a thin soap film. Even though the film appears to be thin, it consists of several molecular layers, and hence it has two surfaces enclosing the soap solution between them. Both the film surfaces are in contact with the wire and hence experience force due to surface tension to reduce their area by pulling the wire, AD, parallel to the surfaces. The net force on the wire due to both surfaces is expressed as F is equal to 2S into L, where S is the surface tension of the soap solution. Now, if the wire is slowly pulled through a distance x to increase the area of the film, the minimum force required is 2SL. The total increase in the area of the film is 2 times L into x. Thus, there is some work done by an external force F in stretching the film, and hence there is an increase in the surface energy. The work done by the external force is equal to F into x. On substituting the terms and simplifying, we get W is equal to the product of surface tension and increase in area A of the film. Thus, we can also define surface tension as the work done per unit increase in area of the liquid surface or surface energy per unit increase in the area of the liquid surface. Thus, the unit of surface tension can also be joules per meter square in the SI system and ergs per centimeter square in the CGS system. The surface tension of a liquid decreases with an increase in its temperature. When the temperature of a liquid increases, the kinetic energy of the liquid molecules increase, and this decreases the cohesive forces. The decrease in cohesive forces results in a decrease in surface tension. We learnt earlier that an increase in the temperature of a liquid decreases its surface tension. This is one reason why we soak dirty clothes in warm water in the process of cleaning them. Also, adding detergents to water or applying soap to clothes makes cleaning effective. Detergents also help decrease the surface tension of water. Dirt in clothes includes grease and oily stains. Water does not wet greasy dirt, as the angle of contact of the oil-water pairing is obtuse. Adding detergent to the water solves this problem. The molecules of detergent are hairpin-shaped. One end attracts water molecules and the other attracts grease molecules, forming oil-water interfaces. Addition of surfactants or surface-active detergents reduces the surface tension of water drastically and hence helps water molecules to penetrate the fabric of clothes and carry away the dirt particles along with them in the flow. This kind of action not only helps in cleaning clothes but also in recovering oil, mineral ores, etc. You have now reached the end of this module. In this module, you learned that force due to surface tension makes a drop or bubble assume a spherical shape. A cohesive force is the force of attraction between the molecules of the same substance. An adhesive force is the force of attraction between the molecules of different substances. The sphere within which molecular forces act on a given molecule is referred to as the sphere of influence. Surface tension can also be defined as the work done per unit increase in area of a liquid or surface energy per unit increase in area of the liquid. The surface tension of a liquid decreases with an increase in its temperature.